We looked at classification and regression problems from a rather general perspectives to begin with. I said a bit about the differences and communalities of machine learning versus and statistical modeling. And I used as examples here simple linear regression, where we also saw first examples of regularization. And also we looked at vector quantization and k-means and its relation to density estimation in this context. Then I talked a lot about the perceptron, and the regular question I get in my lectures in Groningen is, why do you talk about the perceptron so much? Nobody uses the perceptron anymore. Today you will see that it's still one of the most frequently used machine learning algorithm of all, only people use it under a different name, as you will see. So we talked about linearly separable functions, about the classical Rosenblatt perceptron algorithm. I stated the convergence theorem. The proof is in the PDFs that you can get from the web page. We talked about learning in version space, which means we have come up with hypotheses that are perfectly consistent with the training data in order to learn a linearly separable rule, which is behind the data. And then we discussed maximum stability as a criterion for to choose the best perceptron solution if there are many perceptron solutions. And the best is in quotation marks because it's one criterion that is possible, but it's a very useful one because it gives good generalization behavior and it leads to a solvable optimization problem, as we will see today. I presented already one simple algorithm, the so-called minimal overlap algorithm, towards the end of the lectures last time. And today we will look a bit deeper into this. So this is a streamlined version of the full PDF that you find on the web page, but there's also the streamlined version. I've just condensed it a little bit because otherwise I would be running out of time. So here's again the perceptron storage problem, where we have a data set of input vectors and output labels, which are plus or minus 1 in my notation, usually indicating the membership to two possible classes. And the goal is to find a vector W which realizes a linearly separable function that reproduces all these labels in the data set. That we have stated last time already. And we can rewrite this by defining these quantities as to find a vector W which satisfies all these inequalities, linear inequalities. W dotted into the input vector times the output label should be positive or larger equals C, which is a positive constant for all mu. That was the starting point for this perceptron storage problem. So what we're doing here, what we're looking for is a solution to a set of inequalities, which is a bit unusual. Otherwise, we think always in terms of solving equations. Here we are looking for solutions to a set of inequalities. Here they are marked. Now, maybe we can think about the simpler problem again and say, instead of inequalities, why not try to solve P equations for n unknowns? That's something where we feel more familiar about. So we say, let us try find a vector W that satisfies that all these E mu, which are these dot products times the output, equal to 1, that realizes the equations rather than inequalities. Now that's easy to do, right? So first of all, it could be that no solutions exist, no exact solutions exist to my set of equations that I want to solve, so I can at least find an approximation. And the plain vanilla strategy that everybody would think of first is find an approximation by least square deviation. So find the vector W that minimizes a function f, which is the deviation 1 minus e mu squared summed over my set of examples or my set of equations, right? Okay, and I could do this, for instance, by means of gradient descent. Mark has discussed gradient descent a lot, so this is a plain simple example. If I work out the gradient of this function with respect to the weight vector, I get something that looks like this. Sum over data set, 1 minus e mu from the derivative, and then the inner derivative of this guy here gives me the psi vector, the input vector, and the output label. So I could construct my gradient descent based on this gradient, and here we go, and find a solution, an approximative solution of the set of equations, I should say. Case B, the thing is solvable. There is an exact solution, or more precisely, very frequently, there will be many solutions if this is underdetermined. But then we can find a unique solution that satisfies all the equations and gives me minimal norm of the coefficient vector W. That's a reasonable thing to do. So we would have an optimization problem, minimize the norm squared of W under constraints that all the equations are exactly satisfied. Okay? Well, how do we do that? Minimization or optimization under constraints is well known in physics and any other field. We would introduce Lagrange multipliers and define a Lagrange function, which is L, called L here, which is the objective, the norm squared, plus the constraints that I want to satisfy times Lagrange multiplier lambda mu. For each constraint, I need one such multiplier. That's a well-known strategy. And now I can write down necessary conditions for an optimum. And these are, first of all, that the derivative with respect to the multipliers are 0. Well, this just means the constraints are satisfied. And second, the derivatives, the gradient with respect to the weight vector is 0, which gives us this result. W minus the sum of all the examples, lambda mu, xi mu, s mu is 0. Now that's great. What does it mean? It means that W can be written in this way. This is the form of the solution. And you know that already from my last lectures. These lambda mu here, the Lagrange multipliers, which we introduce in an abstract fashion here, correspond to the embedding strength that I introduced last time. Because we can write the solution as a linear combination of the data, and the coefficients are exactly the embedding strength, and they are identical or proportional, apart from some factors n in the definitions, with the Lagrange parameters that are introduced in the constraint optimization. Great. It also means I can go back to my original problem and eliminate W. I can insert this as W into my optimization problem. If I do that, I can, for instance, write the quantities E nu as this complicated double sum, one of them representing the sum over k, the sum over mu, lambda mu times this guy here represents the W vector. The rest is the dot product with the input data and the output. So these are the E nu, and I can write them in this form, and I can define this and call it a matrix element C nu mu, which is dependent only on the data and the labels, and it has index nu from this guy and index mu from that guy. Okay, and I can also rewrite the norm squared using this matrix notation already, and I get a quadratic form in the lambdas, sum over mu and nu, lambda nu, C nu mu, lambda mu. Okay. So everything that is in my optimization problem, I can now rewrite in dependence of the lambdas rather than the W's. And I get rid of the W's, of the weights. And my optimization problem, rewritten, is now, and now we remember that in Lagrange theory, usually if I have a minimization problem under constraints, the Lagrange function is minimized with respect to the original variables, but maximized with respect to the Lagrange parameters. So I have an optimization problem which is maximized with respect to the lambda, this quadratic form, plus sum over lambda mu. This is if you go back to this Lagrange function and you insert everything I just defined, in a couple of lines you find this result. So this is a nice quadratic function with a linear term added to it in terms of the Lagrange parameters. And now I can maximize this by gradient ascent rather than descent. So I need the gradient with respect, or the derivative with respect to the lambdas, here with respect to lambda rho. And if you take the derivative, you get a 1 here, and you get, from the quadratic form, the 1/2 cancels because this is quadratic. I get sum over mu, C rho mu, lambda mu, which is 1 minus E rho. Here we go. So I can come up with a gradient ascent for the Lagrange function, and the change of my, the change of this would be the change of the lambdas in my gradient ascent, right? But the lambdas translate into W's here. So if I change the lambdas, also the W's change, and the change of the W's is exactly this thing. It's the change of the lambdas times the input vector times the output label. That's the definition of the embedding strength. So I recover exactly the same training algorithm for the W's in both cases. In the underdeterminate case and in the overdeterminate case, this procedure here, change the weights according to this step, gives you the solution in both cases. In one case, the unique solution, solving the constrained set of equations, and in the overdetermined case, you find the quadratic, the least square deviation solution, which is also unique. Okay. Now we can, of course, recall or rename our Lagrange parameters embedding strengths. So let's call them x to make this look more familiar, but this is the same slide, just calling lambda x again. Okay. And this would be an algorithm which is fairly simple to implement, and it's called the ADALINE algorithm, and it's one of the classical algorithms in machine learning. Goes back to Widrow and Hoff in the 1950s and 1960s. And here it is in terms of the weights, and here it is in terms of the embedding strength. But these two are the same thing, right? So it's a plain, simple algorithm which checks how far is my E mu away from the target value 1, and this defines then, this tells me how much of this Hebbian type of term I should add to my weights. Okay. Now I can make that more general, right? Instead of having constraints E mu equals 1, I could have constraints E mu equals some value H mu. And still this mathematical structure would be the very same. Just the target value would not be 1, but H mu. And then I could redefine something calling it Y mu, which is H mu times S mu. This is just the target label, which is plus or minus 1. And then this cost function here would become this one. And now this looks like plain linear regression, right? So this is just a special case. The ADALINE is just a special case of linear regression. Nothing more and nothing less. And the gradient-based learning looks very similar to the more complicated neural networks or other nonlinear schemes, only that I here have a linear model, and in the neural network I would have a more complex nonlinear model. Okay. So this is like one of the grandfathers of backpropagation, if you wish, or grandmothers. ADALINE sounds more like a grandmother, doesn't it? Okay. I don't know if the sound works. I just can't help but have to show this movie. So this is 4 by 4 pixels for the input patterns. And I stopped it somehow. And Widrow is demonstrating how this thing learns. Okay, so this is a classical document from, and it's so 1950s, 1960s. I hope you understood what he said. He said, I find my wife's knitting much more complex than this network. This is so 50s, it doesn't get any better. You'll find the link to the full movie on the webpage, and there's a lot more. But what you saw in the end was a multi-layer network. It's a two-layer network. It was a set of linear units, the ADALINEs, in a hidden layer, and then the output of the network was a majority vote of these nodes. So pretty modern concepts already around then. Okay, the J and the T patterns were not as impressive as cats and dogs, and it was only 16 pixels, but you have to start somewhere, right? And this was a hardware realization of this linear kind of network that I just presented to you, which essentially does regression. And this is a very frequent strategy, even nowadays, that you use a regression system, which is originally designed for regression, but you use it for classification by somehow thresholding. So in this J and T case, he said if the reaction of the ADALINE is positive, it's a J pattern. If it's negative, it's a T pattern, or the other way around. But that's exactly what you do. Okay, now we will move on from the perceptron to the support vector machine. So we will look back into the large margin classifier and go beyond linear separability. Okay, here's again the problem that I already showed you, optimal stability. Minimize the norm of W squared subject to inequality constraints. So this is the only difference to the ADALINE problem that I just showed you. Here we have a greater or equal 1, rather than a constraint that says make them all equal to 1. But that gives us more flexibility. In the end, we would find a solution here, W max, and the stability of this thing would then be the smallest of all these E mu, which of course would be 1, divided by the norm of W max. So this would be the stability of the perceptron if we have solved that problem. Okay. Now here's a little bit of notation. I already showed you the correlation matrix C with elements C mu nu, which is just the dot product between data point psi mu and data point psi nu, and then incorporating the output labels S mu and S nu, right? And this would be the full form. I will use vectors with P elements, where, for instance, this X1 is the embedding strength of pattern 1, and there are, of course, P data points, so I have P embedding strength combined into the vector X. And the vector E is the vector of the local potentials, E, that appear in the constraints, and then I use optimization theoretical notation where they always write a vector A is greater than vector B if each component is greater than the corresponding component in the other vector. So this is only done in optimization theory, but you will find it frequently there. And I will use a 1 vector with just a P vector of 1s in it. And then I can rewrite things very conveniently. For instance, the vector E of local potentials becomes just C times X. Correlation matrix times embedding strength. It has these components by definition, so you can go back to the original definition by inserting things, and you see that this is the same. W squared, the norm of the perceptron weight vector, becomes a quadratic form XCX with some decoration in terms of prefactors. Now, this is always non-negative, and C is a positive semi-definite matrix, being a correlation matrix. That's for sure. And here's some other ways to rewrite the norm, if you wish. Okay, and now my optimization problem that looked like this up to now becomes this. I can eliminate the weights because I know that the weights have this form, linear superposition of the data points. And the same problem, just rewritten, is now minimized with respect to the embedding strength, the quadratic form XCX, subject to linear constraints, Cx, all of its components being larger or equal 1. Now this is a quadratic programming problem. It's a quadratic cost function. It has linear constraints, inequality constraints, so that's a bit unusual, but it's still a quadratic programming problem. Minimize a nonlinear function under linear constraints. And you can go to your favorite, this is my favorite book on optimization theory, but you can pick your own, and look up the theory behind it, and what you will come across, for instance, is the Kuhn-Tucker theorem. And normally I don't recommend Wikipedia, but in this case, for a quick start, if you look under Karush-Kuhn-Tucker conditions, you will find the necessary conditions for a solution to this optimization problem. and applied to our problem, which looks like this, minimize the quadratic form under these constraints, you define a Lagrange function which looks pretty much the same as in the ADALINE case, right? So here we have Lagrange multipliers. And the KT theorem, Kuhn-Tucker theorem, tells me that any solution of this problem, which we call a KT point, x star, satisfies the following conditions. Some of them are obvious. Cx larger equal 1 just means we find a solution. We want the linear separation of the two classes. This is this, right? Then KT tells you the embedding strength of the solution will all be non-negative. That's new. That's a new condition or a new insight that we obtain here. Well, we already kind of knew that. If you look back at the Minover algorithm that I showed you last time, that keeps on adding positive constants to the embedding strength, and we start from 0, so the solution has non-negative embedding strength, clearly. But the Kuhn-Tucker theorem tells us this is generally true. And then there's one which is non-trivial and very important. It's called complementarity. It tells us that an embedding strength x star mu times the corresponding condition 1 minus Cx mu. This is the thing that this here should be larger equal 1. So this product of the 1 minus Cx component mu times x mu of the solution is 0 for all mu. So that means either x mu star is 0 or Cx mu is exactly 1. Either one of them has to be true. If you work it out, it also implies that the quadratic form simplifies and xcx becomes x transpose times the 1 vector, just the sum of the x's. This is all pretty much magic, but if you work it out and you apply the KT theorem, you find these amazing properties of the solution of the maximum stability problem. You can use these to also show, which is most important, that all KT points, all Kuhn-Tucker points that satisfy this set of conditions, the necessary conditions for an optimum, correspond to the same weight vector. So any solution that you find of that problem, any quotation mark local solution that satisfies these conditions is a global solution. This is a nice property of the maximum stability problem. You find a solution, you know it's the global solution. That's very rare in optimization. Then you can apply a little bit more of optimization theory. You can eliminate the Lagrange multipliers again, and you end up at something which is called the Wolfe dual in optimization theory, and that tells you the equivalent problem to the original problem is now minimize a function f tilde, which is minus 1/2 the quadratic form plus the sum of all x's of all embedding strength, under the constraint that the embedding strengths are non-negative. The ADALINE problem was exactly the same, but the condition was absent. There we were solving equations. Now we are solving inequalities, and all that changes is this additional constraint on the x's. Hooray, that's easy. We know how to solve the ADALINE problem, right, by gradient ascent. And now all we have to do is the same, but satisfy this condition. How do we do it? Well, we, for instance, sequentially present examples to the system. We perform a gradient ascent in f tilde with respect to the x's. So we would compute the gradient of f tilde with respect to x and perform a gradient ascent step with a learning rate eta, for instance. But we have to watch out that the x's never become negative. So you take your embedding strength x mu when presenting example mu. You add this gradient term, and if this wants to become negative, you force it to get stuck at 0. So you take the maximum of 0 or the updated embedding strength. And this we call the adaptive perceptron or adatron algorithm as one example of how to solve the optimal stability perceptron problem. Okay, and it's quite old, as you see, as I'm quite old. Okay, so we have a rather easy to handle algorithm to solve the problem. It's almost ADALINE, but not quite. Just we have to take care of this extra condition. That's great. Now the complementarity, I come back to the complementarity. That's the key property that the Kuhn-Tucker theorem tells us. It tells us that either x mu is 0 or e mu is 1. So we have either e mu equals 1 and x mu is non-negative, or e mu is larger than 1 and x mu is 0. That's the two options that we have to satisfy these conditions. Now we think back of the geometrical interpretation of the perceptron. we find a plane that maximizes the margin between the two classes. So the filled circles are one class, the empty circles are the other class. The optimal stability corresponds to the plane that realizes the largest gap between the two classes. The support vectors are called the vectors that end up in either this plane or that plane. And they're the ones that have E mu equal 1. E mu corresponds to the dot product of the weight vector with the example, and that's either plus 1 or minus 1. So we have some set of vectors from class 1 that sit in this plane and some set of vectors that sit in this plane. And these are the ones that have E mu equal 1, and more importantly, they have non-zero embedding strength. So they contribute to the linear combination that forms the weight vector. The others have E mu larger than 1, so they are farther away from the decision boundary, either on this side with a positive dot product or on that side with a negative dot product, but they're far away, and they're stable anyway, right? They're classified correctly anyway, and they don't contribute explicitly to the linear combination that defines the weight vector. And that, now you see why these are called support vectors, because they form the support in the linear combination, right? Now, if we knew in advance, looking at the data set, which vectors would be support vectors and which would not, we could simply only use the support vector ones, and we would find the solution to the perceptron storage problem, right? So if these support vectors were known in advance, training could be restricted to the subset of vectors. Unfortunately, we don't know that beforehand. The training finds out which vectors are support vectors and which are not. So that makes the thing more difficult, but still, in the end, we get this very elegant solution that only part of the data is used to support the weight vector, and the rest of the data is accidentally stable. It's not accidentally because we choose the plane to make them stable, but they don't enter explicitly the weight vector. Okay. Now, what we've talked about so far is learning inversion space, including maximum stability as one possible solution. And all this is only possible and only makes sense, obviously, if the data set is linearly separable. At the very beginning, I said, if there is a solution, then the perceptron algorithm finds it, then we can do maximum stability. So if the data set is really linearly separable, we will find that separation, and we will find it with maximum margin. That's clear. Well, but what if the unknown rule is a linearly separable function? That might very well be, but the data set has some examples which are mislabeled. So here we would have the case where in principle it's the same data, but this thing and that thing here has been mislabeled, and now there's no linear separation in my data set. And I'm lost. I cannot apply the perceptron algorithm, but it won't find a solution because there is no solution. And I can't do maximum stability because it doesn't make sense. Even more so, maybe the problem is not linearly separable. Maybe I need a nonlinear boundary to separate the classes. Again, both strategies don't work. So what can I do? So the problems that I might have is that really the target is not linearly separable, or it might even be linearly separable, but the data set is noisy, and that happens in practice almost always, right? So I have a big problem here. So what can we do? Well, one strategy would be stick with a linearly separable function as the solution, but approximate the unknown nonlinear function only by a linearly separable function. And there are many strategies for doing that, and one would be stick with the large margin idea of the maximum stability, but allow for errors. And I will only briefly present this. So we will admit disagreements with the training data, because we know that we cannot enforce 100% correct agreement. There is no version space for that data set. But we keep the basic idea of optimal stability. So we just modify our optimization problem. We say we minimize the norm of W squared, but we add here a penalty term, or an additional term to the cost function, gamma times the sum over beta mu variables. And these beta mu's are called slack variables, and they allow for deviations from or violations of the constraints. So we minimize this subject to constraint E mu larger equal 1, which was the original form, but now we replace the 1 by 1 minus beta mu, and this beta mu is a positive value. So that means if beta mu equals 0, then we are satisfying the good old constraint that we had. If beta mu is positive, then we allow for E mu that violate the constraint, and E mu that becomes smaller than 1, even negative, right? But of course, we don't want that, and we want to have as few violations of the constraints as possible, so we punish the violation of constraints by adding up all the beta mu that tell us how much are the constraints violated and add that to the cost function. So this is like a compromise between maximum stability, which we cannot find anymore, and allowing for errors, for disagreements with the training data. And the gamma here tells us how important are the violations compared to the minimization of the norm. Now you can apply the same tool or the same machinery from optimization theory, rewrite the whole thing in terms of embedding strength. You end up in an optimization problem which also almost looks like the old one. Now we have the quadratic form, we have an additive term gamma beta dotted into the 1 vector, and we have to maximize this subject to these constraints here. The e's are larger equal 1 minus beta, and the betas have to be positive. And after eliminating the slack variables according to the Lagrange multiplier theory, we get to a problem which almost looks like the previous one. We have the same cost function here, minus 1/2 the quadratic form, plus the sum of all embedding strength. Subject to embedding strength are non-negative, but now the embedding strength are also bounded from above. They have to be smaller equal gamma. So it looks almost the same as the maximum stability problem, only now the embedding strength are restricted further. We say they are non-negative, but they have to be smaller equal than gamma also. Okay. And gamma kind of limits here the growth of the embedding strength. So if you have a problem that is almost linearly separable, your training algorithm that assumes linear separability will try to learn and learn and learn and learn and learn and add more support vectors to the weight vector in order to find a solution. So the x mu's will grow and grow and grow and grow. But this here restricts the growth to a certain extent. And then we have to settle for a solution that doesn't satisfy all the constraints because they cannot be cannot be satisfied. And we still find an approximation for the solution. So we have something that looks like maximum stability, but it's not linearly separable, and we have to face the fact that there will be errors, right? Okay. Now, what is unclear now is what in practice I should do with this parameter gamma. How should I set it, right? And one way to find it would be by means of cross-validation, which I hope to have the time to discuss tomorrow a little bit, okay? We should have in mind that this will not find a linearly separable solution anymore. Unfortunately, even if there is one, if I use a non-zero, a finite value of gamma here, I will come up with a solution that has errors, even if there might be one that doesn't. And in general, this strategy does not minimize the number of errors because it takes into account the degree to which a constraint is violated, right? So it's not the same as minimizing the number of errors. Okay. And an example algorithm would be just the good old ADALINE that I showed you, which does a gradient step in the embedding strength, gradient ascent in this cost function f tilde. It restricts the embedding strength to be larger than 0, or at least non-negative, but it also restricts them to be smaller equal gamma. Plain easy to realize. Okay. Now, that was the point, except an approximation by a linearly separable function. For instance, large margin with errors. What else can we do if the data set is not linearly separable? And most data sets aren't, right? Well, we could resort to more complex architectures. We could build a multi-layer network from perceptron units, right? And one can show that such networks can be built to be universal classifiers, not classificators. That's not even a word. So any data set can be implemented in a multi-layer network of perceptron-like units. Only the training is very difficult, and it's not very practical to follow this line of thought. A more popular approach and a more promising approach is that to consider ensembles of perceptrons. So we know that an individual perceptron cannot solve the problem. It can only approximate the problem. but we can have many of those, and then in the end let them decide in a committee kind of way, by majority vote or something like that. So you saw something about this in the lectures by Dalia about decision trees and forests. A forest is, in a sense, an ensemble of trees. Well, that's the definition of a forest, even in the real world. And you can do the same with any other classifier. You don't have to base it on decision trees. Then, of course, it doesn't become a forest if it's not trees. But you can have a committee or an ensemble of perceptron units, for instance. I will not go into this. We could also say, okay, forget about the perceptron. Let's define a threshold classifier which uses on the inside a nonlinear function. So instead of having the sign of the dot product as in the perceptron, a linear function, use some nonlinear function f. Great idea. But which function should we use? This opens so many options that we can choose from. That will be very hard unless we have an insight into the problem and we know that a quadratic function solves the problem. Then we are perfectly happy we can do that. Also, for general f, how do we come up with a reasonable training procedure? It's not that trivial. Okay. Well, the most promising and most successful idea is we will still employ a linear decision boundary, so we can stick with the concept of the perceptron, but we will do a nonlinear transformation of the data. That's in the end, then realizing a nonlinear separation if we find one, right? So we will map the data from n dimensions, the original feature dimensions, to m dimensions, and m could be n, but it's not required. It could be smaller or larger, depending on what we need here, right? And then we could say, okay, if we find a nonlinear transformation from n dimensions to m dimensions, which gives us vectors psi, m-dimensional vectors psi. For each input vector psi in the original space, we find a representation psi in the new space. And if that's then a linearly separable case in the new space, then we can simply use a perceptron in this new space with weight vector capital W to distinguish it from the previous case, which is an m-dimensional weight vector. And then we're back at the perceptron. Only we have to find an explicit transformation that does the job, that gives us a transformed data set which has become linearly separable. And that sounds like impossible, but the nice thing is, it is possible to do that. And that's the idea of the support vector machine. So we have seen what support vectors are in the perceptron in the original case. We will use them also in the support vector machine, that's where the name comes from, where we will apply a nonlinear transformation to a high-dimensional feature space, a higher dimensional feature space than the original space. And we don't even have to do that explicitly. That's the most elegant and exciting part about the SVM. I will show you that. If you go to svms.org, you will find a bit on the history of the support vector machine. And let me point out that it starts in 1963 with a PhD thesis of Vladimir Vapnik. And it took forever and Vapnik to immigrate to the US until it became a practical tool and could be implemented on computers. And the SVM, in close to its current form, were first published in '92, and the soft margin, which is the version that allows for errors, was published in 1995. And Vapnik plays a key role along this trajectory, along this history. So the basic idea is, as I said, employ a linear decision boundary, but after a nonlinear transformation by some function psi that maps every vector psi to a m-dimensional space. And in the SVM, the transformation will be to a higher dimensional space. That sounds crazy, right? Why should I go to a higher dimensional space? Well, because it can make things linearly separable. Here's an illustration that I stole from a former PhD student way back when. We have a two-dimensional data set with components x1, x2, and this would be a nonlinear separation of the two classes, the blue and the red, but we cannot do that in 2 dimensions, at least not with a perceptron. Well, what about a transformation to 3 dimensions? We define psi vector as a function of x1 and x2, which is a 3-dimensional vector, which contains x1 squared, and then here the square root of 2 of x1 times x2, and then x2. So we have here a mixed term that combines the 2 features. What we end up with is mapping these 2-dimensional data points to 3 dimensions, and what you cannot see clearly here, you can see here, Now the two classes have become linearly separable. Now this is a handcrafted transformation, and usually you don't have that insight, but it illustrates the basic idea. By mapping, which seems redundant and stupid, by mapping your data to a higher dimensional dimension, you can make the classes linearly separable. And once we're there, we know what to do. We're back at the perceptron, right? And we can do maximum stability, for instance, there. Okay, so let's assume we have such a transformation that gives us a data set of psi vectors and labels as mu. And if the transformation guarantees linearly separability, let's assume that, then a vector W exists that realizes this. And we can define, for instance, optimal stability. Find a vector W which maximizes kappa of W, where this is the stability in this new space. Same thing as before, only we have done a transformation. We can rewrite this, apply optimization theory, and end up at this new optimization problem, minimize a quadratic form subject to these constraints, where gamma plays the role of the matrix C. So elements of gamma contain are the correlations of the vectors psi in our new space. But the mathematical structure is the very same as before. Plain easy. Okay. And now we can try to be even more elegant. We can say, okay, what I need here frequently are these dot products between the psi vectors. Let's introduce a new name for them. Let's say the dot product between psi of psi mu, one of the examples in the data set, and psi of psi nu, another one in the data set. Let's call that dot product k of psi mu and psi nu. Well, this is just a definition. It's defined as a dot product in the new space for now. So this is a function from Rn times Rn to R. Any pair of input vectors in the original feature space will be mapped to this dot product, which is a real number. Okay. And now I can rewrite everything using this so-called kernel function. The classification scheme was this thing. Well, the output of our transformed perceptron, the new perceptron, is the sign of the W weight vector times the psi vectors in the new space, rewriting W as a linear combination of the data in the new space, which I know I can. I can rewrite W as sum over embedding strength, capital X mu for now, times the psi of psi mu. And now I have here a dot product of psi mu dotted into psi of psi, which is the input to my new perceptron. But this thing here I can rewrite as the kernel function of psi mu and psi. Okay, here we go. We have rewritten the classification scheme in terms of the kernel function. And we can also do the training in terms of embedding strength x mu, as we did in the min-over or in the ADALINE algorithm for the original perceptron. Now we do it for the transformed perceptron. We have capital X mu, and we can write the kernel ADALINE algorithm, that's what it's called in the literature, as such. And here we have the same term as before, only we replace the dot product by the kernel function. Why do I do that? Not just because it looks nice and I like the letter K, but because this tells us that we are not using the transformation explicitly anymore. There's no psi here anywhere. There's no psi, here's no psi, so I can do the training, I can do the classification without using explicitly the transformation psi. All I need is the kernel function K, right? Now, so far the idea was apply a transformation of the data to make things linearly separable. If we have this transformation by means of the definition of the dot product in the transformed space, we have the kernel function K, and then we can do whatever we want with that. Why not turn this around? If we never use the psi explicitly, why can't we just start with the kernel function? Sounds crazy, but why not, right? So we don't need to know psi at all. Not even m, the dimension of the new space. All we need to know is the kernel function. So can't we just define our favorite kernel function and then assume that this corresponds to a mapping that makes things linearly separable? And that's the really brilliant, genius idea of Wapnick that made the support vector machine the support vector machine. So can we start from the kernel and just assume that it corresponds to a mapping that makes sense? Now, you need a few mathematicians to show that this is possible, and you will find conditions on what that the kernel function k has to satisfy to make this a working concept. And there's Mercer's theorem, and I just show it to you. Don't look at it, which is the same as saying look at it, probably. These are mathematical conditions on kernel functions, and if they satisfy these conditions, then we know there is a mapping that can be associated with this kernel function. We don't even have to think about what the mapping is, and we don't even have to think about what M is. Okay, so here are examples for kernel functions that are used a lot in practice. We can use polynomial kernels where the kernel function of psi mu and psi is given as 1 plus the original dot product between psi mu and psi, and this thing to the power q. Right? So if I use that kernel function for the support vector machine, I will get a classifier that looks like this. The output of the new support vector machine will be the sign of this thing here, written in terms of the kernel. Now let's look at them. There's a question.
So if you assume that for a given kernel you always have a mapping, is it unique? So for every kernel you have a unique mapping? Or does it matter?
That's a good question that we should both ask a mathematician. I don't know. For practical purposes, it doesn't matter. Okay. All you need is that there is some mapping. Maybe there's two that correspond to the same kernel, but I have no idea. But I don't care. As long as it makes things linearly separable. Yeah.
So if at the end you only care about the kernel and you can show it for things the reverse condition, it's fine. Why do you need several kernels? Why do you define several kernels?
Because they correspond to differently complex or differently sophisticated solutions. One kernel might not make your data set linearly separable yet. The other kernel might make it linearly separable. That you don't know beforehand. Mercer's theorem only tells you it corresponds to a mapping. It doesn't tell you the mapping makes it linearly separable. That depends on your data set still.
So you can have a kernel, so you can find all the possible kernels and none of them makes it properly separable.
Well, there are some that are guaranteed to make things linearly separable, but that might cause some other problems in the direction of overfitting. Okay. Let's look at some simple examples. The linear kernel. Linear kernel means polynomial kernel with exponent 1. So the kernel is 1 plus the dot product, almost just the dot product in the original space. What does the support vector machine output look like? It's a function sh of the input vector psi, which is the sign of, if you work this out for q equal 1, you get here a constant term, which is just the sum over mu, x mu, s mu times 1. Which I call theta, plus a sum over mu equal 1 to p x mu s mu dot product between psi mu and psi in the original space. What is this? If you can read the small print, you know. It's a perceptron. This is just a perceptron with a threshold in the original feature space. And that's why I said the perceptron is still one of the most frequently used learning algorithms in machine learning. Only people call it the support vector machine with linear kernel because it sounds so much more scientific. But it's not. And it's not at all more modern. It's the same thing. And for years I said, if you use a perceptron, call it a perceptron. But okay, it's too late for that. People call it the support vector machine with a linear kernel. But it's a perceptron. And it goes further. Now people call it the support vector machine. They don't even bother to tell you which kernel they are using, which is sick, because there is no such thing as the support vector machine. The support vector machine is a framework, and depending on which kernel you use, it's a totally different classifier. So don't call anything the support vector machine. It's a concept, not a classifier yet, only together with the kernel. Here's a quadratic kernel, next more complicated thing, q equal 2. If you work this out, you have 1 plus the original dot product squared. You get 1 plus 2 times the dot product plus the square of this thing here, which is a double sum, where you have terms that collect psi j and psi k from the original features. So the quadratic kernel depends on the original features psi j of the input vector and on all products of two features from the input vector. makes sense, right? This is a quadratic kernel. So my support vector machine will be a perceptron that works in a feature space that works with psi1 to psi n, the components in the original feature space. And then I amend to that feature vector all the products of two features from the original space. And I have a linear function in this quadratically mapped space, which corresponds to quadratic separation in the original feature space. All makes perfect sense. What is the dimension? Well, it's the number of combinations that I can form, which is the original dimension plus n times n minus 1/2 because of symmetry, right? Psi1 times psi17 is the same as psi17 times psi1. So this is the dimension, the higher dimension that I went to, hoping for separability there, right? You can go on. You can increase Q. You can use something which looks totally sick, which would be the RBF kernel or Gaussian kernel, almost the same. Use as a kernel function of psi mu and psi the exponential function of minus psi mu minus psi squared, norm squared, divided by some bit parameter sigma. Now, if you think of this in terms of polynomials, if you look at the expansion of the exponential function, you see that this involves all powers of the features in the original space. No limit. So you're going to an infinite dimensional space. If that doesn't sound sick, I don't know what is sick. But this is used a lot and it makes sense, right? So much for the curse of dimensionality as a side remark. It doesn't apply always. The nice thing is, I go to this enormously large feature space, very high dimensional, in the extreme case, infinite dimensional, and I would expect overfitting because I need more parameters in that space. But I always combine this with the idea of large margin, the maximum stability. And that's the regularizing part of it. Because in this space where I have this enormous freedom, I go to this one specific point, one specific solution that has the largest margin. That makes the solution unique, and it makes it simpler again. Okay. So a few remarks. What are attractive aspects of the SVM approach? Well, once I found a kernel that works, the optimization problem is uniquely solvable. There are no local minima or maxima or whatever. I don't have to worry about that. It's quadratic optimization. I find the solution. And this was the strong point in the beginning about the support vector machine. There are efficient training algorithms. Any maximum stability perceptron algorithm you can kernelize and use it for the support vector machine. And maximum stability, that was the starting point of all this, facilitates good generalization ability. And now the but part. Only if the kernel is appropriate, if it's appropriately chosen. So if you use an RBF kernel, then your performance might depend, for instance, on this parameter sigma, right? If you use polynomial kernels, Q equals 3 might work, Q equals 4 might give you overfitting, Q equals 2 might fail completely, right? In practice, what people do now is very often select a rather simple kernel that doesn't make things linearly separable yet, but use a version of the training algorithm that allows for violations of the constraints. And then they introduce the slack variables very much as I did for the perceptron, and you can do the same for the support vector machine. What you do in practice also is you try different kernels if you're not sure what to use, and then you do cross-validation to select the kernel that you want to use. That gives you the best performance, right? The support vector machine has also a problem with very large data sets. Because you're working with the embedding strength, the number of variables that you optimize in the training is one embedding strength per example. So if you have huge data sets, then this becomes costly. But there are approximation schemes that reduce the computational workload a lot. Okay. Here are two books that I would like to recommend on that. Support Vector Machines by Christianini and John Shaw-Taylor. That's hard to read, I guess. And Learning with Kernels by Bernhard Schellkopf and Alexander Smola. Both are very good books that explain support vector machine and also other kernel-based methods in machine learning, which follow the same basic ideas. Back to the support vectors that gave the name to the thing. They are the vectors that end up in the planes. The same applies now in the new transformed space. and they are the support of the weight vector that I need to classify. Okay. So in a sense, the support vectors are the examples in the data set that turn out the most difficult ones, turn out to be the most difficult ones, because they're the ones that are close to the decision boundary, right? So this tells us something about the problem and about the structure of the data set. Typically, if you run the support vector machine on your data set, a fraction of the data will be support vectors, and the others will not be support vectors, right? So you find the difficult ones that you need to define the correct separation, and the other ones are stable by accident, sort of. Now, what if you observe that there are very many support vectors in your data set? Yeah, last slide. Or even all examples become support vectors. Well, what does that mean? That means the classifier, the support vector machine, depends a lot on the details of the data set, right? What does that mean? What are we into or up to? If I change my data set a little bit, I will get a completely different classifier. How does that sound? Not very good, right? It's overfitting. Your classifier becomes overly specific to the data set. And if you use all the data explicitly to represent the weight vector, to represent the separable function, linearly separable function, that means a change of the data set will have an enormous effect on your result. So it means the support vector machine will be overly specific to the data set. That's called overfitting. And possibly your kernel is so powerful that you have so much freedom in your hypothesis space that you need all the data to fix optimal stability in that enormously free space. And that makes things sensitive to changes in the data set, sensitive to noise, and it will destroy your generalization ability. So maybe you should go to a simpler kernel, or allow for errors, or allow for errors. Allow errors to be tolerated in the system. That could give you much better generalization ability in such a case. So we have here a machine, the support vector machine, that already warns you about overfitting, or overfitting over cases where you can expect overfitting without having to do validation. You should still do validation, but it's the first indication that you get as a message from the support vector machine. Now, the support vector machine, the SVM, represents the solution in terms of the difficult cases in the data set. That's essentially the philosophy behind the SVM. You focus on the difficult examples, and the others are correct anyway, so you don't have to work your butt off to make them correct. They will be just correct. Kind of the opposite philosophy to the support vector machine is prototype-based systems. Now, you've seen a lot of prototype-based unsupervised learning strategies. Tomorrow I will talk about prototype-based supervised learning. And there the focus is on representing the data in terms of typical examples. Find a typical example for class 1 and a typical example for class 2. And these are called the prototypes. And then you hope it also works near the decision boundary, but it's a totally different philosophy, you see? Support vector machine focuses on the decision boundary and the examples close to it. Prototype-based methods focus on the bulk of the data and try to find typical examples. Two different philosophies, both have their justification, both have their successes and failures in practice. Okay, that's pretty much it. Thank you. It's the only thing you can do.
One thing. And the other thing is about probability. So how formal it is to consider that the farther the point is from the boundary, for example, it's most probable the classification, or how do you compute uncertainty?
first question, it's the only thing you can do. This is a concept designed for a two-class problem. The way you split up your multi-class problem into two-class problems, that's a different issue. You have choices. You can pick, you can define one problem by saying I want to distinguish class 1 from all the others. And then I distinguish class 2 from all the others, class 3 from all the others. Then you have, if you have C classes, you have C machines, and then you look which one gives you the strongest response in the end for a particular input, and you say that's the class that I accept. You can also do it hierarchically. You can split your classes into the first 3 classes and the last 3 classes and build a tree that ends up at the classes down there. So there are different schemes, and it's almost a religious question which one to use, and it's things that you have to try out in practice. So there's no way out for that. Second question, probabilities. So intuitively, it is clear that the farther an example, an input vector is away from the decision boundary, the more certain the system is about the answer. Can I translate that immediately into a probability? Not so simple to do that. Not so simple. There are schemes like wrapper schemes that do something which is called, I always forget the name, conformal prediction, where you do some sort of complicated leave one out scheme to estimate the probability for misclassifications for a given input, but that's pretty much involved. A direct translation of distance from the plane to probability would be great, but doesn't exist. Further questions? Maybe I can make a remark. I'm old enough to make that. When the support vector machine was big, and it still is, but it had a period where everybody used it. And you couldn't use the word neural networks anymore without being laughed at, because there was the support vector machine. So people said the support vector machine solves classification. Classification is solved, period, that's it. And there were conferences that are called NIP, Neural Information Processing Systems, that had only support vector machine, only kernel-based methods. There was a prize for 100 British pounds for those who would manage to get a paper into the NIPS conference which had the word neural in the title. For years. It was impossible, because everybody said the support vector machine is it, that's it. I'm just telling you this because something similar is happening now, and one should be careful with this kind of statement. Every method has its strengths and problems, and we should never trust too much a new framework or an old framework in the same way. Yeah, that's my personal biased statement about the support vector machine. Okay.